Hi, I'm J Wildberger. Today we're going to start looking at the circular functions, which of course are very important in the standard treatment of trigonometry, but they also are very important in studying circles. And we're going to look at them today with a view of trying to position them, trying to understand where they actually come from and what is their true role. And underlying that is this question of what exactly the definitions of the circular functions are. Okay, so here is a circle. It's the unit circle we're very familiar with. Here's a point on the unit circle. We'll suppose that this angle is theta. And associated to this point are two numbers, the x-coordinate x and the y-coordinate y. So there's a relationship between these three quantities, between theta, x, and y. So as the point moves around the circle, the theta is increasing, while the x and y are kind of moving back and forth in the range from -1 to 1, both in the vertical and horizontal directions. And we try to get at the relationship between these things by saying that x is the cosine of theta. So given a theta, the x value is considered to be a function of theta, and we call that function cosine theta. And the y value is sine theta. So this is how we introduce the circular functions. Now I think it's very important to call them circular functions, not trigonometric functions. They're often called trigonometric functions, and of course there's some other trigonometric functions too, like tan and cotan and then the reciprocals of these ones. But it's really better to think about them as being called circular functions because that more accurately represents what they actually do. They describe the relationship between a point on a circle and the linear coordinates of that point. So underlying here, this is a crucial question. What exactly are the definitions of these functions? So this is an informal description of what's going on, but what's precisely going on? So that's a very interesting question that's in fact full of subtlety and difficulty. So more than 100 years ago, the very prominent British analyst G.H. Hardy wrote a book called A Course in Pure Mathematics, and in that book he talks about the role of the circular functions, and it's very much in the spirit of what we're talking about. He recognizes that there's an essential difficulty about bringing these functions into being in the first place. And this is captured by this relatively famous quote. The whole difficulty lies in the question, what is the x which occurs in cos x and sin x? That's G.H. Hardy in 1908, and he was probably the foremost analyst of that time. He was also famous for having recognized the genius of Ramanujan and getting Ramanujan to come from India to England to study and work with him. Okay, so we have to say something about this. So the question is, what is the role of the angle here? Okay, so we have cosine of something. We think of the something as being an angle, but what exactly are we talking about there? So let us recall that for 2,000 years, the answer to the question, what is an angle, is that an angle is something that's measured in degrees. We are measuring the way around the circle using the old Babylonian system from 0 to 360. This is the system that all the classical tables of trigonometric functions used. Rheticus, but going back to Al-Kashi, Madhava, and then even into the French cadastre and into 19th century tables. Tables would be written in terms of angles. That was the primary understanding of what the relationship was. We're talking about an angle in degrees, and we want to know what is the cosine or the sine. So here are pictorial representations of what appeared in Rheticus's tables. Okay. So we have an angle here going from 0 to 360 degrees, and the sine and the cosine are here. So here in blue is the sine, and here in red is the cosine. So if we have, maybe 110 degrees there, we would read up here and say, oh, the sine of 110 degrees is about 0.83, while the cosine of 110 degrees might be minus 0.71, something like this. Okay. So that is historically the story with the sine and cosine functions, at least. They are functions that look like this. The x-axis, or the independent variable here, is an angle measured in degrees, and the values of these functions are numbers from -1 to 1, corresponding to the x and y coordinates of a point as we move around the circle. So to focus our attention, let's just look at one of the circular functions. Let's look at y equals sine theta and try to understand it and its role. Okay, so here's our circle again, and here's our point on the circle, and there's an angle of theta here measured against the positive x-axis, and it's measured in degrees. And we're interested in the y coordinate of that point. Okay, it's a number between -1 and 1. So what we're really interested in is the relationship between this point as it moves around and the y coordinate, which bounces around between -1 and 1. So let me see if I can show this to you. So here's the point here with the stick, and as we're moving around here, the y coordinate is following along like this, and then it comes back up again there. Okay, so we've completed one round, and the y coordinate has gone up, starting from 0 up to 1, and then back down to -1, and then back up to 0. But it hasn't done it at uniform speed. Okay, so it's not as if it's traversing this uniformly. Here we're traversing uniformly along in an angular sense. We're marching along the circle sort of with uniform velocity, uniform angular velocity. But that's not what's happening to the y coordinate. It's slowing down as the point approaches this point 1, and then as this point here is going through the x-axis, it's going fastest, and then it slows down there again and comes back up. Okay, so if we look at just what's happening there with the y coordinate in the range, theta goes from 0 to 180 degrees, we get this graph here. This is the graph of the y coordinate with respect to the angle, or in this case, almost with respect to time. It's really a time kind of thing if we were imagining a uniform kind of motion around the circle. So here is the classical graph of the sine function. Notably, it's not the same graph that students these days learn about. This is an important point that we're going to have to discuss. Okay, it's not the same graph, but this is historically the sine function. For thousands of years, this is what the sine function looked like. And in fact, even as early as 600, 680 AD, in India, the graph of this function was studied very intensively, and a mathematician called Bhaskara I, so there was also Bhaskara II some centuries later, but Bhaskara I somehow discovered this remarkable formula for an approximation to this function. And he says that sine of x degrees is approximately 4x times 180 minus x divided by 40,500 minus x times 180 minus x. This is a quadratic expression in the numerator, and it's a quadratic expression in the denominator. So this is a rational function of x. So this is not the correct formula for sine of x, but Bhaskara said this is an approximation to it. And it turns out that if you actually graph this, and you can do this on your computer, you can graph this function, and then you can graph the sine function in angles, and you will see that they're almost indistinguishable. You can't tell the difference. It's a very close approximation. In fact, for x in the range 0 and 80, this approximation is within 0.0015 or 16. That's the maximum error between the sine and this quantity here. And in terms of a percentage error, then maybe the error is worse around here. It's about 1 or 2% error at worst. So it's a remarkably accurate formula for the sine. And so you might say, well, if we have this formula, why do we need trig tables? Why don't we just use the formula? Well, the answer is that even though it's quite a good approximation, it's not good enough for astronomical work, for certain types of astronomical work. Because if you're really interested in fine observations, positions of stars, you need to work not just within minutes, but within seconds of arc. And so for that, you really need a very, very precise values for the sine function. And that's what drove a lot of this development leading up to Rheticus, who was after tables to 10 decimal places. He wanted more accuracy because of the astronomical uses. Okay, so what we're seeing here is that this classical form for the sine function, which notably is expressed where you have an angle in degrees, was well understood for a long time. Okay, and it was a sort of a central object of study for a long time in the history of trigonometry. Now we can identify the true role of the circular functions. It really is to connect uniform circular motion around a circle to linear motion of the x and y coordinates of that point. So the circular functions are bridging an important distinction between linear motion and circular motion. They're connecting these two. They're allowing you to translate from one to the other, or take information from one of those scenarios and convert it to the other. But to make this explicit, in other words, to be more precise as to what these circular functions actually are and what they do, we need to decide on the units for both the uniform circular motion around the circle and the linear motion. Now for the linear motion, things are very easy because we're just talking about an x-coordinate going between -1 and 1, or a y-coordinate going from -1 to 1. Okay, so obviously we just have a usual linear scale between -1 and 1, and that's perfectly clear and there's no possible ambiguity. But on the circular side, there is a lot of possible ambiguity because there are different possible unit systems that we could use to measure where we are on the circle. So in particular, we have a choice of the degree system, or we could use so-called radians, or we could use so-called gradients or grads, or we could use something called a turn. So there's a number of different possibilities for measuring along a circle, even if we're interested in uniform motion. So even if we're decided we're going uniformly around the circle, how we're going to describe that, what the coordinate is going to be, is a very delicate question. And there's pros and cons, okay? And you have to make decisions, and maybe some are better than others, and maybe some are better for pedagogical work, and some are better for more advanced applications. So there's a trade-off here. We have to think very carefully about what's going on. Okay, so let's look at these 4 different ways of measuring around a circle, assuming we're intending to go uniformly around a circle. So first and foremost, there's the historically dominant system, which is the Babylonian system of degrees. Okay, that's been around for thousands of years. That's been historically the clear winner, where we measure from 0 degrees up to 90, then 180, then 270. By the time we get to 360, we're back where we started. And there's a lot of advantages to this. I mean, there's no surprise that it's been such a powerful system and been used so much, because it's very nice to have something that's so divisible. So 360 is closely associated to the Babylonian sexagesimal system, where you have base 60, and there's a lot of arithmetical advantages to base 60, in particular that you can divide things more efficiently. You can divide by 5, you can divide by 2, you can divide by 3, you can divide by 4, you can divide by 6. And that manifests itself also in this this degree system, that having this particular system means that dividing an angle into pieces is often quite pleasant. So 90 degrees, you can divide it into 2, you can divide it into 3, you can divide it into 6. Okay, that's a nice subdivision. So then you get 24 pieces altogether corresponding to our calendar or the hours in the day. So it's a very old, established, powerful system with a lot to recommend it. Then we have this system here, which is not so well known at all. So sometimes these are called gradients. So it's kind of a European system where we're adopting a decimal point of view, saying, why should we go from 0 to 90? Let's go from 0 to 100. Okay, that's not unreasonable. Then we'll use a decimal system to divide this segment into 100 different grads, I suppose. And then there'll be 400 all the way around the circle. Okay, and then there's perhaps what's mathematically the most elegant one, okay, which is what you get when you think, well, look, actually we're going around a circle, and there's a natural unit here. I mean, we don't have to arbitrarily impose a unit because there is a natural unit. Namely, you go around once, right? You go around and you get back to where you started. Boom! That means you've got a unit there. It's a distinguished unit. It's very different from lines in space. There's no absolute unit of measurement, but here on the circle there is, because you're getting back to where you started. So why don't we adopt that as a measurement? So we'll measure angles in turns. So this turns, that's what I like to call them, but they're also called revolutions. Okay, there's probably other names too. So here's a turn of 0, and then a turn of a quarter, so it's a quarter turn, and then a turn of a half, and then a turn of 3/4, and then a turn of 1. And that's also quite reasonable. And then there's this other system here, okay, which to a layperson would seem rather curious. If a layperson came in here, it's like an IQ test, which of these doesn't really seem to fit? It's pretty clear that there's something odd about this one. Let's have a look at it. Here we're measuring with an angular system where this has the value 0. And by the time we get up to here, the value is 1.570796326794 ... There's some more digits that I haven't included. Okay, so how far do you have to go before you have the whole thing? Well, you have to go to infinity. Okay, there's an actual infinite number of digits that are left off of here. To get the true value, you need to expend the entire room of the universe, and even then you're only getting started. So you need to go outside the bounds of the universe, whatever that means, and and sort of, I don't know, some kind of almost fantasy or fairy tale, to try to sort of understand what that object, that number is, if it really qualifies to be called a number. Okay, so we've gotten to 1.5707, etc. And now we're carrying on. By the time we get over here, we're at 3.141592653588979 ... Well, okay, we recognize that because, 3.14159, we've heard that before. That is the number that we call pi. All right. That's good. So now we have a Greek letter that we can substitute for this rather painful decimal expansion, which of course also goes on forever. And then we carry on. The angle increases. By the time we're down here, we're at 4.712388980388469 ... Also carrying on to infinity. And then by the time we're getting back to where we started, we've reached 6.28318530717 ... Now I suspect that if we got a jury, of ordinary people from all walks of life, and we sat them there and said, okay, what do you reckon, people? Which one do you think is the best? They'd probably say, well, there's advantages, clear advantages to all of them. I mean, it's been around for thousands of years. It's connected with with astronomy in an established way. It's obviously quite sensible. This one's based on sort of a decimal system. That seems quite reasonable. This seems mathematically very natural. This one, maybe this is some kind of strange concoction that maybe somebody was let out of a loony bin or something. Maybe somebody has smoked too many drugs here or something. How does one work with something like that? So they would probably be astonished to find that in high school we aim to use this system. We say a little bit about this system and say, well, yes, it's quaint and has historical interest, but we really want to get to this system, which is what we really want to do. And interestingly, if we actually got some high school students, even good high school students, or even first-year university students, and we asked them, why is it that we're using this system? What's the reason? I think a lot of them would struggle to give a coherent answer to that. Or the answer would be something like, well, that's what we were taught to do, right? That's what we are learning, and so that's what we get familiar with. And it's not so bad, because once we latch on to the Greek letter pi, then everything is in terms of pi's, and that's just pi by 2, and that's 3 pi by 2, and that's 2 pi. And so the complexity can be almost forgotten about. And when we need to address the complexity, well, our calculator does it for us. Okay, but of course there are reasons why this system is used. It's not some perverse kind of thing. It's because this particular system meshes well with analysis. Okay, so another player enters the story. So traditionally we have astronomy. That was the main player, the main motivator for trigonometry. And then we had geometry, another key motivation for trigonometry, understanding a circle. But now we have a third player, which is analysis, basically calculus and its extensions. And from a calculus point of view, there are certain theoretical advantages in framing the sine functions, not in terms of angles or grads or turns, but in terms of these radians. That's the radian story. But in fact, that point of view has only been around for a couple hundred years. It's not really historically very deep. And it's certainly the case, I think, that young people who are just aiming to finish high school and get mathematics under the belt, they really do not need a trigonometry based on radians. They just don't. They do need to understand uniform circular motion, and we will talk about that some more in our next video. But it doesn't have to be framed in terms of radians. The advantages of that are only more apparent when you get to sort of second-year university level and you start doing some Fourier analysis. But we'll see that you can do Fourier analysis very nicely also without having to deal with transcendental issues. And also, unfortunately, having the pi's everywhere means that there's a lot of places where pi's end up being involved where they really don't need to be involved and unnecessarily complicate things and connect with a transcendental aspect that you don't really have control over. Namely, really what we're talking about are these infinite decimals, these numbers that go off to infinity, which really renders us outside the realm of pure mathematics. Okay, so interesting stuff. I want to talk next time more about this, the radian system, and why is it that we use the radian system, and what are the alternatives? And in particular, I'm still interested in high school mathematics and addressing the question of what should they learn in the context of uniform motion, which is really coming from physics. So we'll talk about those things in our next video. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.